Everyone, and welcome to this explainer. Today, we're going to break down the biggest buzzwords in artificial intelligence, and we're going to look straight under the hood to see exactly how machines are taught to learn. We hear terms like AI, machine learning, and deep learning thrown around interchangeably all the time, right? But understanding the actual mechanics behind them, well, that's what separates the casual observer from the truly informed learner. So let's get into it.
We've got a lot of ground to cover today. We're going to unpack AI, ML, and DL, map out the machine learning process, dive into deep learning networks, compare rule-based versus learning-based approaches, and finally, look at how machines actually learn.
All right, Section 1, Unpacking AI, Machine Learning, and Deep Learning. Let's clear up these massive buzzwords once and for all.
So instead of thinking of these as competing technologies, just picture them as nested Russian matryoshka dolls. Artificial intelligence is that biggest outermost doll. It's the broad, overarching field of creating machines that simulate human intelligence like reasoning and problem solving. Pop that doll open and inside you'll find machine learning, which is a specific subset that enables systems to learn from data without explicit programming. And if you open that doll, you find the deepest, most advanced layer, deep learning, which relies on incredibly complex artificial neural networks.
To really make this stick, think about what they're actually trying to achieve. AI is the broad vision. You're aiming to train a general, intelligent behavior. Machine learning is the practical method, where you're training a system to automatically improve its predictions using data. And deep learning? That's where you're training a highly complex model capable of processing massive, non-linear datasets.
Moving right along to Section 2, the machine learning process. How do these systems actually pull this off?
Now, before we look at the pure mechanics, we really need to understand why this matters. The concepts we're about to discuss are the exact same technologies diagnosing diseases from medical images right now, suggesting your next Netflix binge, and allowing self-driving cars to navigate real-time city traffic. It's literally transforming how every single industry operates.
So the big takeaway here is that getting to those incredible real-world applications, it isn't magic. It requires a highly structured 7-step pipeline for turning just raw, messy data into incredibly accurate predictions.
Let's walk through the first 4 steps of this pipeline, using a super classic example, teaching a machine to recognize cats. Step 1 is data collection. First, you have to gather thousands of images of cats and, just as importantly, non-cats. Step 2 is data pre-processing. You can't just throw raw data at a machine. You've got to clean it up, maybe resize all the images to be the exact same dimensions, and handle any weird missing values. Step 3 is choosing the model. So for images, you'd probably pick a convolutional neural network. And step 4 is training the model. This is where you actually feed that pre-processed data into the algorithm so it can start associating specific features like fur texture and pointy ear shapes with the label cat.
Okay, let's see how this builds into the final stages. Step 5 is evaluating the model. You test your algorithm on completely unseen data to check its accuracy. If it's suddenly mistaking dogs for cats, well, you move to step 6, fine-tuning. This is where you go in and adjust the hyperparameters, things like the learning rate or the number of layers in your network, just to improve performance. Finally, when the accuracy is high enough, you reach step 7, prediction. You can now feed the model a brand new, never-before-seen image, and it's going to successfully predict whether a cat is in the frame. Boom.
All right, Section 3, Deep Learning and Neural Networks. Time to open up that final, deepest nesting doll.
It is just absolutely fascinating to see the direct inspiration for this technology. When you look at a biological neuron from the human brain, you have dendrites receiving signals and axons transmitting them. And then you see how we've mathematically mimicked that exact structure to build artificial neural networks. We are literally modeling artificial processing after our own human biology. It's wild. Just like billions of neurons fire in our brains, these artificial networks use interconnected nodes, and they are strictly organized. You've got an input layer that receives the raw data, one or more hidden layers where all the complex mathematical transformations happen, and an output layer that delivers the final prediction. By stacking these layers super deeply, these networks can process massive data sets. In fact, while a human brain has roughly 100 trillion synapses, some of today's largest deep learning models are already boasting over 1 trillion artificial parameters. 1 trillion?
Which brings us to Section 4, rule-based versus learning-based approaches. Let's look at how AI modeling has evolved.
So back in the old days, developers had to rely on a rule-based approach. This was very deterministic and static. A human developer literally had to sit down and write explicit if-then instructions for the machine to follow. The problem? That is not scalable for complex, real-world tasks at all.
But in the modern learning-based approach, the whole paradigm completely flips. It becomes probabilistic and dynamic. The machine is fed raw data and the desired outputs, and it actually discovers the hidden patterns and designs its own rules to connect the two.
For example, imagine trying to write traditional rule-based code to describe an apple. You'd have to code the exact hex colors, the mathematical curves, the stem, and honestly, it's pretty much impossible. But with a learning-based approach, you simply feed the system 100 labeled images of apples and 100 labeled images of bananas. The system analyzes the pixels and extracts those distinguishing features entirely on its own. The labels themselves act as the guide, allowing the machine to build its own internal logic.
Okay, final section, Section 5, how machines actually learn. Let's break down the 3 main methods.
The first, and definitely the most common method, is supervised learning. This is exactly like our apple and banana example. You're training the algorithm on a strictly labeled dataset. You provide the input, and you provide the correct answer, the output. The machine learns the mapping between the two. This task-driven approach is exactly what powers things like spam email detection, where millions of past emails have been explicitly flagged by humans as either spam or not spam. Next up, we have unsupervised learning. And honestly, this one is much wilder. Here, you're handing the machine completely random, unlabeled data. There are no predefined categories, no right answers. The algorithm just has to explore the dataset completely unguided and autonomously figure out the hidden structures. A great real-world example of this is customer segmentation in marketing, wherein AI groups purchasing behaviors together without ever being told what those groups should look like.
Finally, we've got reinforcement learning. Think of this as a feedback-based technique where a digital agent learns purely by interacting with an environment. It is trial and error on a massive, massive scale. The agent makes decisions, and it receives positive rewards for good actions and negative penalties for bad ones. Over time, it develops a policy to maximize its long-term rewards. This is the exact underlying tech that allows systems like AlphaGo to master incredibly complex board games, or self-driving cars to navigate city streets.
So, as we wrap up this explainer, we're left with a pretty profound realization. We are moving so far away from rigidly programmed machines and stepping into an era where artificial systems are directly mirroring human biological learning. By processing data to design their own rules, they are continuously evolving. The real question we have to ask ourselves now is, as these networks get deeper and the datasets get larger, what unprecedented capabilities will these systems be mastering tomorrow? Thanks for joining me on this deep dive into the mechanics of AI, and keep learning.